In the last video, we saw that if we wanted to take the derivative of two functions that are being multiplied, we cannot just take the derivative of each piece. That never works. But we did state that we could take the derivative by using this really weird formula. Now, as we're going to see throughout all of this kind of second unit, that every time we come across a derivative rule, we want to justify it, right? How do I know that this is the rule? I mean, is it the rule just because I put it in a box and I said so? Like, no. Why is that the rule? Why isn't it something else? Well, what's really nice is that we can actually go ahead and actually try to prove that if I take the derivative of a product, I actually end up with this all the time, regardless of the functions. Now, of course, if I want to be able to prove this, I'm going to have to go back and start using the definition of the derivative. So let's go ahead here and start seeing what's going to happen as we calculate the derivative. So I'll state here, we calculate the derivative using the definition. So we're going to start here by computing d dx, so that's the derivative of one function times another, by using our big scary limit. Okay, so remember how the big scary limit setup actually worked. It said I have to take what I'm going to be doing the derivative of and first plug in x plus h for all the x's. So that would look like this. F of x plus h, g of x plus h. Then I have to subtract the function with just x plugged in. So that's f of x, g of x, and then I divide everything by h. Okay, so great. What the heck do I do with this? I mean, this looks terrible. How in the world can I get from here to here? Well, maybe we can simplify something, right? I mean, obviously we can't plug in 0 right away because we're going to divide by 0, but is there anything I can like factor from the top or simplify out? Gosh, this is really messy. There's nothing up here that's in common. What the heck are we supposed to do? This is where this next move in the argument becomes unbelievably surprising. Like, you really got to hand it to the person who makes this next move. Take a look at what's going to happen here. What I'm going to go ahead and do is I'm going to take the numerator of this fraction, and I am going to add something to it. Now, you might object to that right away, kind of saying, wait a minute, Kyle, you can't just add whatever you want to the top of the fraction and have it be the same fraction. And you would be right. You can't add whatever you want. But there is a value that you can add so that the top of the fraction would maintain its current value. The number 0 could be added. So take a look. I'm going to go ahead and I'm going to add in the number 0 here. I'm going to write it in red. Here's how it's going to look. I'm going to start by actually subtracting f of x plus h times g of x. And then I'm going to go ahead and add f of x plus h times g of x. The rest of my fraction is going to look exactly the same as it used to. It's only this red part that's been introduced. But hopefully you would agree that that red stuff is a grand total of 0. I added 0 to the top of my fraction. Okay, so why in the world would I do that? What's the advantage of adding nothing? Well, if you take a look at what I'm able to do now, you could see that if I was to group together these first and second terms, and then these third and fourth terms, I could actually see that now there are some things that I could begin to factor out. So take a look. In the first set of brackets, can you tell what's in common? Well, yeah, I have an f of x plus h that's in common, and a g of x plus h minus g of x would be left over. I can do the same thing with the second set of parentheses, where I have a g of x in common. And I'd have an f of x plus h minus an f of x left over. And all of this is still going to be over h. Now, I'm going to have to combine several steps now into one to try to squeeze this all in the space that we have remaining. But here's what I'm going to do in the next step. If you take a look here, you might be able to see that since I have now kind of two things being added, that is, I have all of this stuff over here at the left, added to all this stuff at the right, and since it's all divided by this value of h, I could separate my fraction into two different fractions. I could do the whole first part over h and the whole second part over h. But then, if I have two fractions being added or subtracted, by our limit laws, I could rewrite this as a limit of the first fraction. So let me go ahead and write this out. Here's the limit of my first fraction plus the limit of my second fraction. So this would be g of x times f of x plus h minus f of x over h. Well, if I can evaluate then each of these individual fractions, this should be pretty easy to go ahead and simplify all the way down. Well, I'll be able to finish this off now in one final line. Notice that here, I can actually separate this fraction a bit further, in that I could actually go ahead and imagine separating out that f of x plus h and pulling it off of the fraction to kind of write it by itself in the front. So I'm going to go ahead and re-express it now to look like this. I could just have, f of x plus h being multiplied to what I have here. And if I have a limit of two things multiplied, I can just take the limit of each piece. So f of x plus h. And then my limit here of g of x plus h minus g of x over h. Similarly over here, I can pull the g of x off, and I could separate that into two separate limits. But even easier, notice that since h is the variable that's being moved by this limit, and g of x has no h's in it whatsoever, it acts like a constant. And so I could actually just pull it right outside of the limit using my limit laws. And so I'd be left with f of x plus h minus f of x over h. Well, if I take a look at what I have here, I think I can simplify this out by evaluating each limit individually, and I'll get a final result. Notice here that if h here is headed to 0, then this is really going to look like f of x plus 0. Notice that I'm essentially moving my limit past the f function to the inside. And I know I can do that because the function f is continuous. Wait a minute, how do I know that my function f is continuous? All I was told is that my functions were differentiable. Well, if you think back to our sections on continuity, you might recall that if a function, or sorry, not our section on continuity, but our section on differentiability, that if a function is differentiable, then it must be continuous. So I can actually do the limit of the inside of this, and that would leave me with just f of x. Now, if I take a look at this limit right here, you might recognize, wait, isn't that kind of like the big scary derivative limit that we've been working with for the past several sections? And yeah, it is. So I could just rewrite that as g prime. Finally, over here, I can write this as g of x times, and this would be f prime of x. And if you look at what we have right here, you'll notice it is a perfect carbon copy match of what we have up here. The only thing that maybe even slightly appears different is that I have a different order in terms of the multiplication over here. But one of the great things about the product rule is that since it's only built using multiplication and addition, we can rearrange the order of those things very, very easily. So multiplying things in opposite orders always creates the same value. And similarly here, I could even have had these things added in a different order. I would still generate the same value. So this is really, really great. We can actually see exactly why this must be the rule for when I multiply two functions together and then try to take their derivative. In the videos to come, we'll try to practice using this on some different functions.